Welcome back to AI.Code.Cast. Today, we're going to be taking a deep dive into a classic coding challenge that honestly trips a lot of people up, and that's level order traversal of a binary tree. So imagine you have this tree-like structure, and you need to visit every single node in it, but level by level and from left to right.
Yeah, it's kind of like reading a book, but instead of going line by line, we're moving across levels of nodes.
Okay, so let's say we've got just a basic binary tree. Just to be sure we're all on the same page, could you maybe walk us through what a brute force approach to this problem might look like?
Sure, so the most intuitive approach that comes to mind is to simply go level by level, right? You start at the root, visit that, then move on to its children and so on.
So just systematically visit each level.
Yeah.
Seems simple enough, right? What's the catch?
Well, the thing is, without a systematic way to keep track of things, it's really easy to miss nodes or even visit them out of order, especially as the tree gets larger and more complex.
So this brute force method, while appealing in its simplicity, could lead to some pretty messy code, potentially even some errors.
Exactly. We need a more robust way to make sure we process all the nodes at a given level before we move down to the next one.
So how do we achieve that? Any hints?
Okay, think about data structures that are designed for processing elements in a specific order. What comes to mind when you need to handle things in a first in, first out manner?
First in, first out. Sounds like we need a queue.
You got it. A queue is the perfect tool for this.
Okay, I'm intrigued. How does a queue actually help us with level order traversal?
So picture this. You start by adding the root node to the queue. Then, as long as that queue isn't empty, we're going to follow a simple set of steps.
Okay, lead the way. I'm all ears.
All right, first we peek at the queue. We do that to see how many nodes are currently in line. This tells us how many nodes we need to process at the current level.
Interesting. So the queue size defines the boundary for each level.
Exactly. Now, we dequeue each of those nodes one by one, and for each node we dequeue, we visit it, meaning we perform whatever operation we need to on that node's value.
Got it. So far, so good.
And now comes the crucial part. After visiting a node, we unqueue its left and right children, if they exist, of course.
Ah, that's clever. By adding the children to the back of the queue, we ensure they'll be processed in the next round. That way we maintain that level-by-level order.
That's the key insight. We keep repeating this process, check the queue size, dequeue nodes, visit them, and enqueue their children, all until that queue is completely empty.
This queue-based approach sounds so much more systematic than that brute force method.
It really is. And by using a queue, we guarantee that we're traversing the tree in the correct level order, which minimizes the risk of errors.
Now, I'm curious about the efficiency of this approach. How does it stack up in terms of time and space complexity?
Well, in terms of time complexity, it's very efficient. Since we only visit each node exactly once, the time complexity is O(n), where n is the number of nodes in the tree.
Okay, that sounds pretty good. And how about space complexity? Are we using up a lot of extra memory with this queue?
So the space complexity is also O(n) in the worst case scenario. This happens when you have a very wide tree, where the queue could potentially hold all the nodes at the widest level.
So while it's efficient in terms of time, the space usage might be something to consider depending on the structure of the tree.
That's a great point. It's always a good idea to consider the trade-offs between time and space complexity when you're choosing an algorithm.
This queue-based level order traversal is definitely a winner in my book. But you mentioned earlier that there are other ways to solve this. What other approaches should we be aware of?
Well, there's another approach that leverages recursion. While the iterative approach with a queue is generally preferred because of its efficiency, recursion can offer a different, maybe more elegant perspective on this problem.
Recursion. Always a bit mysterious, yet alluring. I'm definitely curious to see how recursion can be applied to this level order traversal problem.
Let's explore that further. So the core idea is to traverse the tree recursively. But this time, instead of using a queue to keep track of the levels, we're going to pass the current level as a parameter to our recursive function.
So each recursive call is essentially focusing on a specific level.
You got it. Each call handles a specific level, adding the current node's value to that levels list in our results, and then it recursively calls itself for the left and right children, increasing the level by 1 for each call.
That's an interesting way to manage the levels without explicitly needing to use a queue. But like any recursive function, we need a stopping point, right? How do we prevent infinite recursion in this scenario?
That's where the base case comes in. The recursion stops when we hit a null node, and that indicates that we've reached the end of a particular branch. This makes sure that the recursion will eventually terminate.
So this recursive approach is providing a different perhaps more elegant way to achieve level order traversal, and we don't even need a queue. But you mentioned trade-offs earlier. What are the potential downsides of going with this approach?
Well, while recursion is often praised for its elegance and sometimes even readability, it can have implications for space complexity, especially when we're working with trees that are really deep.
Could you elaborate on that? When does this recursive approach become problematic in terms of space?
In the worst case scenario, where you have a very deep, unbalanced tree, the recursive call stack can grow quite large. Each recursive call adds a frame to the call stack, and if the tree is really deep, this can actually lead to a stack overflow error.
So for very deep trees, the iterative approach with a queue might be a safer bet.
Precisely. In cases like that, the iterative approach is generally more space efficient and less prone to those stack overflow errors.
Okay, so we've got these two distinct approaches, the queue-based iterative method and the recursive method. It seems like choosing the right one depends on the specific situation and the characteristics of the tree we're working with.
Absolutely. Understanding the trade-offs between those two approaches is key to making an informed decision.
Okay, so we've covered these two main approaches to level order traversal using a queue and recursion. Now let's maybe shift gears a bit and talk about some of the common pitfalls that developers might encounter when they're tackling this problem.
Yeah, so one common question that often comes up is what happens if the tree is empty?
Ah, the good old empty tree case. It's like the blank canvas of data structures. How do our approaches handle this scenario?
Both the iterative approach with a queue and the recursive approach are designed to gracefully handle an empty tree. They would simply detect that there's no root node and then return an empty result, which is typically an empty list.
Okay, that's good to know. It's always important to consider those edge cases. Are there any other tricky situations that we should be aware of?
Another potential pitfall is making sure you're handling null nodes correctly, especially when you're working with the recursive approach.
Yeah. Null nodes can be tricky. Why are they particularly challenging in recursion?
Well, in recursion, it's really important to have that gets case that checks for null nodes and stops the recursion if it encounters one. If you don't handle those null nodes correctly, you could end up with an infinite loop or some other unexpected behavior.
Right, we definitely don't want our code to spiral into an infinite abyss. Speaking of connections, I remember learning about breadth first search, or BFS, in the context of graph algorithms. Does BFS have any relation to level order traversal?
It's not just a relation. Level order traversal is essentially BFS applied to a tree structure.
Whoa, so we're secretly doing graph traversal without even realizing it. That's pretty cool. So what are the implications of this connection? Does it mean any BFS algorithm can be applied to trees?
That's a great question. While level order traversal is basically BFS on a tree, there are some nuances to consider. Trees are a very specific type of graph, so not all graph algorithms would translate directly to trees. However, this connection really highlights the fact that the principles of exploring a structure layer by layer apply to both graphs and trees.
I see. So understanding BFS in the context of graphs gives us a much deeper appreciation for level order traversal in trees. Are there any real-world scenarios where this connection becomes particularly valuable?
Absolutely. Think about things like network routing, right? You might need to explore all the nodes at a certain distance from a source node before you move on to nodes that are further away. That's a classic BFS scenario, and the same principle applies when you're working with hierarchical data that's represented as trees.
Wow, this deep dive is really illuminating the connections between these seemingly different concepts. Now, let's say we want to take this level order traversal idea a step further. Instead of just visiting each node, what if we want to find the sum of the values at each level?
That's a great way to extend the concept. So instead of ending up with a list of nodes, we'd get a list of sums, one for each level. How do you think we could modify our queue-based approach to achieve this?
Let me think. We could still use the queue to process nodes level by level, but instead of just adding the node's value to our output list, we'd need to keep track of a running sum for each level.
You're on the right track, so how would you maintain those running sums?
Maybe we could create a separate list to store those sums. Each element in the list would represent a level. As we dequeue nodes, we could add their values to the corresponding level's sum.
Yeah, that's a great approach. And once you've processed all the nodes at a given level, you just append that level's sum to your final output list.
So it's the same basic structure with the queue, but we've added this extra layer of calculating sums for each level. Now I'm wondering, how would we adapt the recursive approach to handle this sum of levels problem?
Modifying the recursive approach to calculate sums might seem a bit trickier, but the key is to figure out how to pass information about the running sum down through the recursive calls.
So instead of just passing the current level as a parameter, we'd also pass the current sum for that level.
Exactly. Each recursive call would get the current level and the sum that's been calculated so far for that level. Then it would just add the current node's value to that sum.
And then when we hit our base case, that null node, we know we've reached the end of a level, and we can add that level sum to our list of results. It's like we're building up those sums as we traverse down the tree.
You got it. So the recursive approach, while maybe a bit less intuitive for this modification, can definitely still be adapted to handle this sum of levels problem really effectively.
It's amazing how we can just tweak these fundamental algorithms to solve different but related problems.
That's the beauty of algorithm design, understanding those core principles and then applying them creatively to new challenges.
We've covered so much ground in this deep dive. We explored level order traversal, its two main approaches, those common pitfalls we talked about, and even its connection to BFS. What are your final thoughts for our listener?
The key takeaway I want people to walk away with is to think beyond just memorizing these algorithms. Try to understand the underlying principles behind them and why certain approaches might work better in specific scenarios. It's not just about memorization, it's also about thinking about where these concepts show up in real-world applications. It's one thing to understand an algorithm on paper, but it's a whole different level to see how it's being used to solve real problems.
Right. Where does this level order traversal actually pop up in the real world?
So one area where this is commonly used is anything that involves representing data in a hierarchical way.
Could you maybe give us some more concrete examples?
Sure, think about file systems. They're inherently hierarchical, with directories containing subdirectories and files. You could actually use level order traversal to list all the files and directories level by level, starting from the root directory.
So it's like exploring a file system in a really structured, breadth-first manner.
Mm.
What other applications can you think of?
Oh, there's so many. Level order traversal is used in network routing algorithms. Sometimes you need to look at all the nodes at a given distance from a source node before moving on to nodes that are farther away.
Wow, it's really amazing how this seemingly simple concept has applications in all these different areas.
It really is. Another fascinating example is in game development. Imagine a game that has a map with different levels or areas. Level order traversal can be used to generate or explore that game map level by level.
That makes a lot of sense. It ensures that players encounter all the challenges and content in a logical order.
Exactly. And those are just a few examples. You'll probably encounter level order traversal in many unexpected places as you continue your coding journey. There are endless possibilities.
This deep dive has been so insightful. We explored the ins and outs of level order traversal, compared different approaches, talked about potential pitfalls, and even connected it to broader concepts like BFS and real-world applications.
It's been a pleasure discussing this with you. And remember, the world of coding is constantly evolving. There's always something new to learn and explore.
Absolutely. To our AI.Code.Cast listeners out there, keep experimenting, keep learning, and never stop exploring the amazing world of algorithms. Until next time.